A very important part of the knowledge about electromagnetic wave is it has two components, electric component and magnetic component, and those components perpendicular to each other. And that leads to a very important property. This is a mechanical model of a phenomenon which we call polarization. So, all I need to do is have a kind of long slit, and also I'm going to need, would you please help me? I need someone to, yeah. Let's hold this. That's it. So you know, we can easily generate a wave on a string. All we need is a string and wave it. So here, if I excite this end of this string, the wave easily getting through. All right. Now, please hold it. Try not to move it. And I'm going to try to excite this wave in the direction perpendicular to the slit. So the wave is traveling toward the slit, but it cannot get through. So when the wave is moving in the direction parallel to the slit, it's getting through easily without any, thank you, loss of the energy. However, when the wave is perpendicular to the slit, that's it, it stops. It cannot get through. Now, we can apply this mechanical model to electromagnetic waves. What I have here this is, well, it's a simple radio. It's a source of electromagnetic waves. And this is a receiver connected to a little amplifier. So the wave is traveling from here to here, and the sound tells us that wave actually is reaching the receiver. Well, no sound. Now the wave is missing the receiver. Now, I can cover, I can place, well, that's not a slit, just a piece of metal. What is happening? Why we don't hear anything anymore? Because it isn't absorbed completely by this piece of aluminum. But now, instead of using a piece of aluminum, I can use this grid. It's kind of several slits. Yeah? So, what's going to be happening? when they start moving, they interact with atoms around. Well, it's kind of friction between electrons and atoms. Atoms take energy away from electrons, and this thing becomes slightly warmer, but not very warm. Energy cannot be lost completely. However, so electric component of the wave loses energy to electrons, electrons lose energy to atoms, and there is no wave after this grid anymore, but only when well, these rods are horizontal. When these rods or slits are vertical, wave easily travel through, right? So, my first question. In that particular experiment, what do you think is the direction of electric field? Is it vertical or is it horizontal? So, for the vertical electric field, you can press 1, and for horizontal direction, for the electric field in that particular wave, electromagnetic wave, you can press 2. Now, let's see. No luck today. Well, I knew that would eventually happen, but why today? All right. Just raise your hand. Well, let's see anyway. So if you think the direction of the electric field in that wave is vertical, would you raise your hand? And horizontal? And could you please tell us why?
Me?
Yeah.
Because the magnetic field would be perpendicular to that.
Well, as I said, a wave loses its energy when electric field can easily move electrons along these rods, right? So, a wave loses its energy when rods are horizontal. That means electric field should be horizontal. In that case, force acting on electrons also is horizontal, and electrons easily move back and forth. When electric field is perpendicular to the rods, in that case, the force is perpendicular, but there is no room for electrons to move in that direction. So electric field doesn't do much work, and the electromagnetic wave doesn't lose much energy getting through. Now, well, this is a mechanical model. We now can apply this model to a light, because light, as we saw, is an example of electromagnetic wave. However, for the light, we can immediately derive a very simple expression for electric field before that kind of device and after. So, let's say, well, these rods are horizontal. This is one of these rods. And let's say this is the direction of the electric field in a wave traveling into the screen. So the velocity c points into the screen. Well, magnetic field is supposed to be perpendicular to electric field and velocity. Magnetic field is not of importance for this situation because it doesn't act much on electrons even if they move. So what is happening? We just saw if we resolve electric field into two components. One component is parallel to rods, and another component is perpendicular, right? So what's happening? This one, which is parallel, doesn't get through because it loses its energy. And this one, which is perpendicular, travels through. So this device does two kind of jobs. Number one, it changes the orientation of electric field, because after this device, the electric field must have a specific orientation. Only this component travels through. Plus, the amplitude of electric field changes. So that's what the initial amplitude, that's the amplitude after this device. Less amplitude means less intensity. So the intensity of electromagnetic wave, including light, before this kind of device and after changes. And for the light, we don't have to use aluminum grid like this. For the light, we can use a specific transparent materials like this. A material like that has normally long molecules which act in a similar way. So each material like that has a specific direction. If electric field is parallel to that axis, to that direction, it travels through easily. And if electric field is perpendicular, it doesn't travel through. And if electric field is at some angle, only partially, only portion of a wave travels through. So for a situation like that, when we have a polarizer, a device like that we call a polarizer, and the direction in which the wave is traveling through without any loss in energy, we call transmission axis. Light wave transmits through this device without loss in energy if electric field oscillates in that particular direction. So this is a transmission axis of this polarizer, transmission axis. And again, now we can consider electric field, well, at arbitrary angle to transmission axis. Now, again, we can introduce two components. One component is parallel to the transmission axis. One component is perpendicular to the transmission axis. The perpendicular component is getting cut off. It cannot get through. The component of the electric field parallel to the transmission axis getting through. And that component is proportional to the initial amplitude of the field times cosine of this theta, this angle. This is the right triangle, the hypotenuse, and the component which is traveling through the polarizer. And if you remember, the intensity of light, or any wave, is proportional to the product of electric field and magnetic field. And magnetic field also is proportional to electric field and electromagnetic wave. So intensity is proportional to field squared. That means the intensity of the light is supposed to be proportional to cosine squared. So that's it. That's what we call the Malice's law. If you have a polarizer, and if your electromagnetic wave is initially polarized in a specific direction, in that case, the intensity of this wave after the polarizer equals intensity of this wave before the polarizer times cosine squared of the angle between the transmission axis and electric field. Or direction of the electric field we also call direction of polarization of wave. Well, so this is an example of a situation when the light is initially polarized. A regular light from a regular bulb has electromagnetic waves with all possible directions of polarization. So One wave has electric field like that, another wave has electric field like this and like this. This kind of light we call unpolarized. So we just said, if polarized light traveling through a polarizer, to calculate what happens to intensity, we have to use the Malus's law, cosine squared. What is happening to this light when it's traveling through? Well, let's say the direction, the transmission axis is vertical. In that case, this wave travels through with no loss in energy at all. And that wave doesn't get completely. And some waves in between getting partially through. If we add up all the intensity, on average, we get the result that for unpolarized light, the intensity of the light after the polarizer equals 1/2 of the intensity before, between 0 and maximum, half. Well, now we can play with these things. Well, first of all, now we can take a look at better pictures of what I said. So, unpolarized light, polarizer, transmission axis. As we said, a polarizer does two jobs. It changes intensity, so intensity is equal to 1/2 of the initial one, and it polarizes light. Now, all the waves which are through must have the same direction of polarization. For light which is already polarized, when it travels through a polarizer, again, the intensity is different. It's related to cosine squared of the angle between the transmission axis and the direction of polarization. Plus, again, light becomes polarized in a different direction. So after the polarizer, light is always polarized in the direction of the transmission axis. Well, before we go to this example, so you can take one little thing, this rectangle, just take a look at the light. Try to rotate it. Well, first of all, well, I have just a bigger version of this. You see that if you look through this rectangle, the intensity changes. Here. Where is it? Here. The light is brighter than here. The polarizer changes intensity. It's constant half. Bright, not so bright. And you can see it. Now, if I rotate this device, do you see any changes? Not really. What we know is that light must become polarized after traveling through this device. But how could I prove it? In that case, I would need to use a second polarizer. Because now, if you take two of them, and now if you look at the lights through two and you start to rotate, you can see how intensity actually changes. Well, I have a larger version of this experiment. That's a second polarizer. So we can place it on the top of the first one. And now I can rotate it relative to each other. Oh. When it's completely dark, what does it tell us about the angle between transmission axis number 1 and transmission axis number 2? What angle? It's supposed to be 90 degrees. Because in this situation, what is happening is, so, well, initially unpolarized light. It is traveling to the first polarizer, and it becomes polarized in the same direction. When there is no light, it means the second polarizer has transmission axis perpendicular 90 degrees to the transmission axis. So there is no light after the second polarizer. Well, there's a question I want to ask this question right now here. So we don't have now any light getting through the set of two polarizers. Last. I have, you don't, but I do, one more polarizer, number 3. So my first polarizer is this. My second polarizer right now in this, and I don't have anything yet in between. So there is no light here. We don't have to use a photocell to detect it. We can use our eyes, no light. The question is, if I take this polarizer and if I place it in between, is there going to be some light traveling through this set of 3 polarizers? Well, you think about it, and I give it one more try. It's working. All right, so if you think that when I place the third polarizer between these two, there is some light traveling through the whole system, you can press 1. Otherwise, you can press 2. A and B work the same way as 1 and 2. And of course, maybe you still answer until, oh, maybe the last question, the previous one, I don't know. Well, first of all, it's a physics, so we can actually run this experiment and see what's going to happen. All I have to do is take it, polarizer, and slide it between these two. First, let's make sure no light. No, 90 degrees. And now, we can see some light now is actually getting through the system. Why? Well, because now we don't have 90 degrees angle, neither for the light and the first polarizer, or between the light and the second, or between the light and the third. What we should draw is a picture like that. Well, so intensity, of course, changes. And more important in this situation, that direction of polarization changes too. So after the first polarizer, light is vertically polarized. However, this polarizer changes the direction of polarization, and now after the polarizer number 2, light is not perpendicular to the third transmission axis anymore, and the angle is not 90 degrees, so cosine is not 0. Well, now let's do this example. So, 2 polarizers located along the x-axis, each at 30 degrees to the vertical axis. Unpolarized light is traveling from left to right, and we have to compare the intensity of the light after it travels through the whole system and before. So, initially unpolarized light is traveling through the first polarizer? Well, if this is the initial intensity, the intensity of this light after the polarizer has to be equal to a half. For unpolarized light, it's always a half of the initial one. So 1/2 of the initial one. But more importantly, it becomes being polarized in the direction of the transmission axis of the first polarizer. So now, this intensity, final, supposed to be equal to intensity of the light just before this polarizer, which is 1/2 of the initial, times cosine squared of what? Of the angle between the transmission axis and direction of polarization. And what angle is it? That's going to be my additional question to you. System is working. I can ask you now as many questions as I like. So, 30 degrees, 60 degrees, 90 degrees. These are your possible answers. Just in case, make your mind, because I have to erase it. So, 1 for 30, 2 for 60, 3 for 90. And now let's because this is the most important part. What angle should be plugged in? You plug in the correct angle, you get correct result. You plug in the wrong angle, you get a wrong result. That's it. And 60 degrees is the right answer. Because if you look at this picture, now what? So, if you look at this picture, from that perspective, what you see is one axis pointing like that at 30 degrees to the vertical in one direction, and another axis like this at 30 degrees to the vertical in opposite direction. So the total angle is 60 degrees. It's very important sometimes to choose the right way to look at the system. Well, so we'll answer this. Well, situation, and there are many more possible questions. For example, what if light is initially polarized? Well, it would be something like this. Light is linearly polarized with polarization direction 20 degrees to vertical, and has an initial intensity 16 watt per meter squared. And again, we have two polarizers. It says a pair. First polarizer is angle at 50 degrees, the second is the angle at 30 degrees. Exactly the same situation as we just did. The only difference is the light is initially polarized. So, the easiest way to solve a problem is draw a picture. Again, you have two polarizers. Well, that's the vertical axis. This is the transmission axis for the first polarizer, 50 degrees. And this is the transmission axis for the second polarizer, 20 degrees. And, well, I'm going to give it a try. Light is initially polarized at 20 degrees to the vertical. Usually, when the angle is represented by a positive number, well, Professor Tucker at least, means that it's measured clockwise. And if you want to say that the transmission axis or direction of polarization is in opposite direction, in that case, we would use a negative number. Technically, it doesn't matter because only relative values are matter. So in this situation, all numbers are positive. So this is our case. And what we see is that initially the light is polarized at 20 degrees, and the first polarizer has exactly the same transmission axis. What does it tell us about the intensity of the light? It doesn't change. Well, formally it means that the angle between transmission axis and direction of polarization is 0. Cosine of 0 is 1. So for that particular orientation only, the first polarizer doesn't do anything to the light. So it's getting through, having the same intensity, and only second polarizer does something to it. What does it do? Two things. Number one, it polarizes it, so changes its direction. And number two, it changes the intensity now. How? Well, now the intensity after is supposed to be the intensity before, which is, as we know, supposed to be 16 times cosine squared of the angle. Which angle? Between the direction of polarization, which is this blue line, and the transmission axis, which is this one. And this angle is 30. It's 50 minus 20. So the picture tells us what to do. Well, cosine of 30 is square root of 3 over 2. We square it, it's going to be 3 divided by 4. So that has to be 16 times 3 over 4. That's an example of a calculation. Very common calculation in a problem like that. So even if your function is kind of square root of something, you square it anyway. So you have a nice number to deal with, and calculations are relatively easy. Now, well, this is another possible situation to consider. In our examples before, we have to solve a straightforward problem. There is a light of a specific polarization, specific intensity, polarizers, again, with specific orientations, and we want to figure out what's happening in the end. An inverse problem sounds like if you want to have a specific intensity in the end, how would you choose the orientation of your polarizers? Okay? And in the end, what could we do? Well, we could cut it completely. We could maximize intensity. We could minimize intensity. How would we maximize intensity? How would we minimize intensity? Well, this example, this experiment tells us if we want to maximize intensity, for example, so what do? We would like to have the angle between transmission axes as small as possible. The extreme situation when there is no angle. In that case, light travels through without any change. What would we do if we wanted to minimize intensity? Well, minimum intensity is 0. And it happens when the angle between the transmission axis and direction of polarization is 90. Well, if by some reasons we cannot make it 90, still we would have to make it as close to 90 as possible to minimize the intensity. Well, another typical problem. Let's say we start from the situation when both polarizers are parallel to each other. The direction of transmission axis is the same for both. And we start, well, this light is unpolarized, and we start rotating one polarizer relative to another. And we make one whole revolution. 360 degrees. How would you draw a graph which represents the intensity of the light getting through as a function of the angle between the transmission axes? So take a minute and try to make a sketch of a graph like that. So again, what is happening? We start from two polarizers with transmission axes parallel to each other. The light is initially unpolarized. Then first polarizer comes, then second polarizer comes. And what we do, we rotate the second polarizer by 360 degrees. The intensity of this light as a function of the angle, we know it changes. So how would your graph look like? This is one. Well, you should draw your own version. This is another possible situation. This is another, and I could draw more. Let's say this is case number 1, this is case number 2, this is case number 3. Okay, so take a minute, draw your graph, make your mind, choose a number, 1, 2, or 3. Because I have to erase it. Okay. What's wrong with this thing? Keeps. Well, at least I've learned how to fix it quickly. Well, the easiest and the fastest way to choose the right graph would be to kind of choose which graphs are wrong first. Well, first of all, when we start from a situation when axes are parallel, we start from the maximum possible intensity. So the graph number 1 cannot be correct because it starts from 0 intensity. Plus, intensity is amplitude of the field squared. If you square anything, you always get a positive number. Intensity cannot be negative, so the graph number 3 doesn't work either. So only the graph number 2 works. You start from 0 degrees, you start from maximum intensity. You go to 90 degrees, no intensity, it's 0. But you keep moving, so when you reach 180 degrees, you reach a maximum intensity again, then 0 again, and then the maximum intensity one more time.